One is Maxwell frequency and another one is damping ratio. And coming to the damping ratio, when there are three cases, when damping ratio zeta is equal to 1, okay, right, and then damping ratio 0 and damping ratio is equal to, very much greater than. So there are 2 to 3 cases we consider, correct? So based on that, we classified system as undamped systems, underdamped systems, overdamped systems, so on. So based on zeta, right? So here, this is what example, here omega n is 4 and then zeta is 8, 0.5. So this is what we have seen. There are two poles and we discussed and we defined pole also. So overdamped, underdamped, okay, where the roots are complex conjugate, and undamped means the pole lies on the imaginary axis. Critically damped, the poles are the roots are real roots and lies on this real axis. Okay, right. So now, if it is a second order system, all four cases need to be seen. One is undamped and underdamped. Okay, underdamped and then overdamped and critically damped. So all four cases need to be seen, and we consider input as a step input. Okay, right. So now, when we try to see the system behavior, we try to characterize the system. A second order system response would be like this, right? So characterization done by using few parameters, right? So we will discuss those parameters little later. So this is what the S plane, right? So undamped frequency is what we said. So now, can anyone tell like what are the, yeah? So these are the roots, right? Right. So this is what the characteristic equation S square plus 2 zeta omega ns plus omega n square. Right. So when you try to find out the roots, can anyone tell me what are the roots? Minus b plus r minus under root b square minus 4ac by 2a. So now tell me what are the roots? These are the roots. Minus omega n zeta plus omega n under root zeta square minus 1. Right. So now, can I write this as minus omega n zeta plus r minus j under root 1 minus zeta square? Can I write like this?
Yes, sir.
Okay. So the roots are this. So real part is omega n z. Imaginary part is under root 1 minus zeta square.
Just omega, sir.
Omega n. Yeah, correct, correct. So minus omega n zeta plus r minus j omega n under root 1 minus zeta square. So this is what we try to write it as minus omega n zeta plus r minus j omega d, where d is omega n into under root 1 minus zeta square. So now if you try to understand the physical meaning of this, okay, if you try to understand physical meaning of this, right, and if you try to represent this on S plane, right, if you try to represent this as omega, so this is what zeta omega n, no? Yes or no? This is the real part, no?
Yes, sir.
Omega n zeta. and imaginary part is omega d. So if you try to represent that on S plane, so this is minus omega n, and this area, this is j omega d, where omega d is nothing but what? This distance is what? Omega d. This distance is what? Zeta omega n. Understood, no?
Yes, sir.
Right. So then what about this? You know this. You know this.
The hypotenuse, sir, the distance.
So what is that you are going to get? If it is zeta omega n, and then this is omega n under root 1 minus zeta square, then this is this. So what about this?
Omega n.
Omega n. So is that verified, all of you? So this is omega n. So omega n is what we are calling as natural undamped frequency. Try to understand from now onwards. If we are not able to understand the system behavior in time domain, then we are applying Laplace transform, and we converted that into S domain, and then in S domain we try to understand the behavior of the system. So one term which we came across is natural undamped frequency. Okay, natural undamped frequency. So omega n is this. So when you define omega n, how can you define now? So the distance from the origin of S plane to a pole is natural undamped frequency, and it is in radians per second. Is yes or no? So the radial distance of this particular pole from the origin is defined as natural undamped frequency. Is it not? Okay. So if the poles are like this, then omega n is this. We call the circles as omega n circles. If omega n is changing, right? So this is with 3 radians per, so let us draw a circle of radius 3 in S plane. So 3 radians per second. So like that, S plane is divided into constant natural undamped frequency circles. Is this all right now? Is it
Yes,
all right? Yeah.
yes, sir.
So now then we try to understand zeta. What is zeta? So now this is zeta omega n, right? And then this is j omega d, right? So what is cos theta?
Zeta.
Zeta.
So or otherwise, what is theta? Theta is cos inverse zeta. Zeta is cos theta, right? So how do you define this damping ratio? The damping ratio is the cosine angle, okay, cosine angle of that pole to the real axis. Yes or no? The cosine of the angle between vector connecting origin and pole and negative real axis yields damping ratio. Is this understood now? So there are two terms. One is omega n and another one is zeta. So in S plane, we try to understand this. Right. So omega n is the radial distance of the pole, the complex pole from the origin. And whereas zeta is cosine angle of the vector connecting origin and the pole and the negative real axis is called this zeta. Right. So for underdamped systems, the poles are complex conjugate where zeta lies between 0 to 1. And for undamped system, zeta is 0. Right. When zeta is 0, the pole lies on the imaginary axis. Is it not? So pole here, when you try to see this, minus omega n zeta plus or minus j omega n under root 1 minus zeta square. Right. So when, yeah. So here, now, when zeta is, okay, when zeta is 1, Then when zeta is 1, the roots are real roots, is it not? When zeta is 1, this part is 0, roots are real, correct, no?
Yes, sir.
And when zeta is 0, when zeta is 0, roots are
Complex, sir.
imaginary. The roots lies on imaginary axis, correct, no? Yeah. When zeta is lying between 0 to 1, the roots are complex conjugate roots. Okay, right. So and now we have to analyze this. Yeah. So now if you try to see this zeta omega n and this, okay. So now where we try to see the cases, and if yeah, if zeta is
For overdamped system,
over dam, the critical dam system roots are real, no?
overdamped, sir, zeta greater than 1.
Well, for zeta is equal to 1, roots are real, no?
Yes, sir.
Right. If zeta, if it is very much greater than 1, roots are real or complex or lies on the imaginary axis?
Real.
Real. But they are little bit away from imaginary axis, is it not?
Yes, sir.
Yeah. So we will try to consider that cases, no problem. Now, in this case, now let us try to take step response of a undamped system. Okay, step response of a undamped system. What do you mean by undamped? Zeta is
0.
0. When zeta is 0 and input is step, is it not? Right. So then C of S is equal to what? Omega n square by S square plus this term, what it become? 0, no? Zeta 0, no?
Yes, sir.
So omega n square by by S square plus omega n square. And what is R of S for step input? Unit step.
1 by S.
1 by S. So here it is 1 by S. So now what we want? We want C of t, no? So when we want C of t, what we should do?
First Laplace transform.
Now tell me what is inverse Laplace transform of this case? Omega n square by S square plus omega n square. Inverse Laplace transform is what? Sin omega nt or cos omega nt? What inverse Laplace transform?
Sin omega.
Try here, try. It's not there here. Try.
Sin omega.
Now 1 by S is also there. No, what is C of t? One minus sin omega nt. Tell me. 1 by s is also there, no? What do you get? 1 minus cos is this the response?
1 minus cos omega t. Yes, sir.
1 minus cos omega t. Correct, no? Yeah. Now, what we need to do, we want time response analysis. Time response analysis means when t is equal to 0, what happens? When t is equal to 1, when t is equal to the next one, how it happens and all is what we know, right? When t is 0, how you get the response? Tell me. Anadam thoroughly we discussed, but this you try to do. So, or otherwise by seeing this expression, what you can say? By seeing this expression, when zeta is equal to 0, means what? There is no damping. When there is no damping, then what happens? The response is oscillatory, is it not? See here, we want time response analysis, means with various values of time t, we need to plot the t. So now here, this is 1 minus cos omega n t. So now when t is 0, what is the response? When t is, when t is increasing, how is the response? Okay, so here you will be getting a response, a oscillatory response, is it not?
Yes, sir.
This is what you are going to get. Cosine waveform, no? So clear cut derivation, I'm trying to search for clear cut derivation, but I don't think so. This is second order response, second order response. So the total time response, now if I try to see damping when it is 0, Yeah, so this is what the response you are going to get. Is it okay? So this is what the response you are going to get. So by seeing the inverse Laplace transform itself, we can say like okay. So I hope now you can understand. The C of t here in this case so when it is under damped case, you are going to get this the response as okay. We are going to get the response C of t as 1 minus cos omega n t for various values of t. If you try to plot, you are going to get a response like this. Okay, is this fine? So what
Sir,
we can
why it's not touching 0 again? Only,
Which
only
one?
in the graph, sir.
Hmm.
Only once it is touching the 0 at the origin.
Fellow, what it is having here? Which type of waveform it is? Sine or cosine or what?
Sine.
Then
Sir, when cos becomes 1, then the equation C of t will be 0 again.
which case it is becoming then? For various values of omega n only, various values of t only we are trying to see, right?
Yes, sir.
And t infinity, try to see the plot. Okay. So the conclusion is, if a system is undamped, okay, when the system is undamped, or when zeta is equal to 0, and if the input, if it is a step signal, the system will always oscillate with its natural frequency, natural undamped frequency. Understood? Is this understood? Class 10th is 57. Very good. So this time more supplementary candidates I am expecting. Okay, right. Abhinav Reddy,
Yes, sir.
is this understood now?
Yes, sir.
Okay. So when system is undamped, means when zeta is equal to 0, and zeta is equal to 0, then the system will always oscillate with its undamped natural frequency, is what the conclusion is. So this is the case which is undamped. So now we try to consider the case underdamped. When we try to consider a case underdamped, then zeta lies between 0 to 1, no? Okay. So when zeta is lying between 0 to 1, and if you try to simplify this, so step response, so R of S is 1 by S, and zeta lies between 0 to 1. And you try to see this 1 by S. Okay. Right. So S square plus 2 zeta omega ns plus omega n square. Okay. So you can write this as A by S plus BS plus C by S square, and then if you try to find out the partial fraction, then you are going to get the expression like this, partial from partial fractions. So now when you apply, inverse Laplace transform, then you can write this as S plus 2 zeta omega n, right? So I'm just adding and subtracting a term, right? Zeta omega n square and minus zeta omega n square. Can I do it like this?
Yes, sir.
Yeah. So then the finding out the values, anyhow partial fractions and all you can do, no problem. So now how can we write this now? S square plus 2 zeta omega ns plus zeta square and omega n square. So can I write that as S plus 2 zeta omega n whole square? You can write no?
Yes, sir.
Yeah. So then, and from this, and this, anyhow, we can omega n square if we try to take common, 1 minus zeta square. Okay. Right. And then now if you further simplify, understood, no? Now, if we try to write this again as omega n square into 1 minus zeta square. So we wrote omega d as omega n into under root 1 minus zeta square. So we can write it as omega d square, no?
Yes, sir.
Yeah. Now, something we can write this as, s square plus, omega n square by s square plus omega n square. So inverse Laplace transform, there is a standard notation for this. So here if I write this as s plus zeta omega n plus zeta omega n, can I write like this, no?
Yes, sir.
This term. And then if I further do simplification, 1 by s minus s plus zeta omega n by s plus zeta omega n whole square plus omega d square minus zeta omega n by s plus zeta omega n whole square plus omega d square. I think this is a standard form, right, for inverse Laplace transform. This is inverse Laplace transform of it. 1 minus e power minus zeta omega n t into cos omega dt. So this is like cos omega dt, no? E power minus zeta omega n t cos omega dt. Okay. And e power minus zeta omega nt sin omega dt. Okay. Understood?
Sir, in the third term, the zeta by root 1 minus zeta squared, that doesn't need to be changed. Oh, it's not a constant. Okay, got it.
Right. So now we will just simplify this further. Okay, so when we simplify this further, e power minus zeta omega nt is what common? Cos omega dt. Right. Cos omega dt. Right. So now this, when you try to simplify it further, right? So now if you simplify it further, if you bring if you bring this term here under root 1 minus zeta square, so e power minus zeta omega nt by, right, omega nt by under root 1 minus zeta square. So under root 1 minus zeta square, if it comes here, into cos omega dt plus zeta sin omega dt. What is zeta? Can I write zeta cos theta?
Yes, sir.
Yes, sir.
And under root 1 minus zeta square. So if you try to simplify this, okay, if you try to simplify this, what you can write, this term is C of t is equal to 1 minus e power minus zeta omega nt by, okay, under root 1 minus zeta square cos omega dt plus theta. Cos A plus B.
Sin, sir.
Sin, sir.
Sorry. Sin omega dt plus theta. So sin A plus B is what?
Sin B plus cos A sin B.
So this zeta is what you can write cos theta sin omega dt, okay, plus anyhow cos omega dt is here under root 1 minus zeta square. So under root 1 minus zeta square, what you can write from here? So this is zeta omega n. This is omega d. This distance is d, omega d. Right. So this is what the distance, and then this is what the distance omega d. Okay. Right. So under root 1 minus zeta square, what you can write?
Sin theta.
You can write here sin theta under root 1 minus zeta square here.
Sin theta.
So sin theta. So we can write this as sin theta cos omega dt plus theta is anyhow cos theta and sin omega dt. So we can write this as sin A cos B plus cos A sin B. What we can write? Understood, no? C of t is equal to 1 minus e power minus zeta omega nt by under root 1 minus zeta square sin omega dt plus theta. Okay, So it is a exponential decaying sinusoidal function. Right. So exponential decaying sinusoidal function. So then if you try to write, zeta from 0 to 1 and then vary omega n, then the response, you would be getting response like this. Okay.
Okay, sir.
Right. So now we conclude zeta is equal to 0 means undamped system. So undamped system means which will always oscillatory in nature. The moment you give step input, which infinitely always oscillates, is that there is no system of that kind. In reality, we find. Is it not? Any system, after giving input, it reaches its final value, right? Yes or no? Do you get any system will always oscillatory only spring, no? The moment you give input, correct, no? So all real-time systems are underdamped systems. Underdamped system means whose zeta lies between 0 to 1. So then if you give an input, right, if you give an input like step input and leave, then the system will exponentially increasing and then it will stay. So I am giving an input of step input. So the input, in the beginning it will be, uh, dynamically changing. What we call it as transient response. And after some time, it will be in the allowed limited range, which is called steady state response. Okay, steady state response. The total time response of any system is transient, means initially it will be changing its response and it will be staying within a given range. It's called steady state response. So transient response and steady state response is what called total time response of a system. So any system, the moment you give input, it will be changing its response for some time and it will be staying within the limited or allowable range. This is what the conclusion is. All real-time systems are underdamped systems and those systems response would be of this kind. Okay. Now if a system is of this kind, then we need to do characterization. So what do you mean by characterization? Yeah. So now here in the response is when zeta is 0.5 and omega n is 3, the system is having response like this. When zeta is 0.9, omega n is 3, the system response is like this. Okay, so this is what the underdamped system response. Right. So now, by varying the zeta value, this is what you are going to get the responses. Yellow color one, zeta 0.9 means you are getting response like this. Out of this, which is good system or which is a desirable system? With your knowledge, can you tell me?
The yellow line one?
Yellow line, yellow line means, here we want a input. We gave input 1, but here output is beyond 1, no?
Yes, sir.
That means, now let us take, there is a vehicle suspension system and there is a road bump. And when there is a road bump, the passenger is hitting, means, the bus is oscillating so that the passenger is hitting on the top, which is called oscillations. right? So or overshoot. So these systems should be characterized by certain parameters, and few are called transient response parameters and few are called steady state response parameters. What do you mean by that? So in transient response, when you give input, the system, when it is changing its output, we characterize them using certain parameters called rise time, overshoot, settling time, delay time, and so on. What do you mean by that? So now let us try to understand this. Okay. So now if you try to take a system like this, I gave one input like this. So one system behaved like this. Okay. And one system is behaved like this. Okay. And another system's behavior is like this. So this is system 1, this is system 2, this is system 3. Which is better?
3.
3. So system 3 is better. Right. So then we need to characterize. What do you mean by characterization? Now if you try to see this response and this response and this response, we use a term called rise time. So what do you mean by rise time? The time taken by the response to reach 10% to 90% of its final value is called rise time. I repeat, rise time is defined as time taken by the response to reach 10% to 90% of its final value. So now let us take here, it is, to go up to 90%, let us take, it is taking 5 seconds. And now let us take, it is 3 seconds. And this is taking, let us take 1 second. Out of these 3, which is better? The third system is responding within 1 second, it is reaching 90%. No.
Yes, sir.
So then this system is better. So we try to characterize the system response, right, by using this. So it is called this is called rise time. The time taken for the response to reach 10% to 90% of its final value or 100% of its final value is called rise time. And delay time. Delay time is defined as time taken by the response to reach 50% of its final value. Peak time. The time taken by the response to reach maximum peak of the maximum peak value is called peak time. Delay time, rise time, peak time. 3 terms. And there is one more term called overshoot. We want 1, but we got much beyond 1. Right. So this overshoot is defined as, now 1 minus this is called overshoot. Yeah. So these are called transient response parameters, and settling time means the time taken by the response to reach 98% or 102% of its final value. That means sometimes 2% of band is what had allowed. Few systems 5% band is allowed, means 98 to 100. So here 98 to 102 is okay. So it can settle down 98 to 102% of its final value. The time taken for the system to reach 98% to 102% of its final value, and it will stay there only 98 to 102, 98 to 102, and that kind of response is called, the time response is called settling time. It is settled down to its final value. Rise time, delay time, peak time, settling time, and overshoot. These 5 parameters are called transient response parameters, and derivation of these and a few problems we can solve in the next class based on this. If you have any questions, you can ask me, or otherwise you can attend your next.
Sir, I have one question. Overshoot is not desired, or is it? I didn't understand that.
Yeah, we will much explore this by taking different examples. Generally 5% of overshoot is what allowed, not more than that.
Okay, sir.
Okay, so it is undesired only, right? Designing of a controller is to reduce the overshoot. That is what a control system engineer goal.
Yes, sir.
So here we got overshoot. Sometimes we got undershoot. Few systems exhibit undershoot. Means few systems will exhibit like this.
Okay, sir.
So we'll be characterizing about these second order systems in the next class. Okay, so all of you, you try to do this derivation of underdamped system and then you keep it ready. Okay, so we will be seeing the behavior of the system in the next class. Okay, all right. If you have any further questions, you can ask me. What is your next period?
3 o'clock, sir.
3, na? So let me take 1 or 2 minutes only and then conclude. Yeah. From the responses what we have seen, for a good system, how should be the transient, how should be the rise time? Rise time should be less or more. A good system should exhibit rise time less or more.
Less.
Yeah. So a system with minimum rise time is good system. Correct? Means what? It is responding within no time to the input, no?
Yes, sir.
Yeah. And delay time, a system which exhibits delay time should be less, means a system is fast, means it should have delay time less or more?
Less.
Less. And what about settling time? Settling time should be less. One system settle down within 5 seconds, another system settle down within 2 seconds. Which is better?
2 seconds.
2 seconds. So a system should have overshoot 0 or some value. Which is better?
0.
One system is having like this here. So there should not be any overshoot, no? Correct, no? So how to design systems is what this control system tells. Sir, now we are EC engineers where we are using. Now you are designing a CRO, cathode ray oscilloscope, on which you can view waveforms. Now you switch on your CRO, then the CRO is, that blinking rays are coming. One system is taking 1 minute to blink the system, another one is within 10 seconds you are getting rays on the CRO. Which is better? Or television, you have television, right? When you switch on power supply, immediately you should get picture, right?
Yes, sir.
But when olden days, I think it takes time, right? When you switch on, it takes, and I think at least 10 seconds, 20 seconds to switch it on, right?
Yes, sir.
So this rise time is the characteristics of how your system is fast is indicated by using this particular time parameter, and we will be discussing about this in the next class. Okay. All right. Thank you.
So in general, it's preferred to have all quickest times, rise time, delay time, settling time.
Being a control system engineer, if you design any device or anything, you have to design this the rise time 0 is what the goal.
Okay, sir.
Means within no time it has to respond to the input.
Okay, sir.
All right.
Thank you, sir.